Hello, oceanography students. This is your final video um, recording for the atmospheric circulation topic. There is one video left to watch after this, and that is on hurricanes. So let's get started. Right. So what we talked about previously was all large-scale circulation patterns and global climate. But we can also have air circulation on a regional or a smaller scale. So that's what this lecture is on, and it includes information about weather. Okay, so we can see a daily change in wind patterns in areas that have a large body of water close to them. And these two images are showing you that. In the top image here, we have a coastal area during the day. So during the day, we have the sun beating down on the water and on the land. Now remember that water has an extremely high specific heat capacity, which means it takes a lot of energy to raise its temperature. Land does not have a high specific heat capacity. It changes temperature very quickly, as you can tell if you go to the beach and you walk on the sand and it's really hot, and you go to the water and it's really cold, right? So what happens is the land warms up very quickly, and therefore that warm air above the land lowers in density, and therefore it rises up. When air is moving away from Earth, air from someplace else is going to rush in and take its place. So the air that is from the water, which is nice and cool, comes in and takes its place. And so in the late afternoon, after you've had an all day of heating the land, you end up having what's called a sea breeze, which is wind blowing from the ocean onto land. Now at night, now we take the sun away, the land is now going to cool down, and it's going to cool down more rapidly than the water is. And so what that creates is cold, dense air that sinks down. That creates a high pressure zone, and at high pressure zones, air is always going to want to move away from it towards lower pressure zones. So what we end up with is air sinking over land and air rising over water, and a net flow of wind from land towards the water at night, or probably early morning after it's been dark all day. Okay, and again, that's due to the difference in the specific heat capacity between water and between land, that on a very small scale, we have a daily reversal of pressure zones where it becomes low pressure over land towards the end of the day, and then it becomes high pressure over land towards the end of the night. Okay, now we can look at this in a slightly larger scale as well, where we can compare the seasonal changes in high pressure and low pressure and what that means to our wind patterns. So during the winter, the land is cooled down much more rapidly than the water is, and therefore where land is cold, that means that the air above it is dense and it's sinking. So high pressure cells develop, which are shown here on land in the northern hemisphere. So this image here is showing us northern hemisphere winter and southern hemisphere summer. So during the summer, now we have sun beating down and the land warms up very rapidly, and therefore we have low pressure over land with air rising up, and then we have high pressure over the water with air then sinking. It's always going to be reversed. When it's high pressure over land, it's going to be low pressure over water, and when it's low pressure over land, it's generally going to be high pressure over water. Okay, and so in places where it's low pressure versus high pressure, we actually have wind that's circulating around that low pressure zone or around that high pressure zone. And the direction that it circulates is based on the high pressure versus low pressure, and also it's based on the hemisphere. Okay, so in the northern hemisphere, air circulates around a high pressure zone clockwise and around a low pressure zone counterclockwise. In the southern hemisphere, it's reversed. Around a high pressure zone, air circulates counterclockwise, and air circulates clockwise around a low pressure zone. We call airflow around a high pressure zone anticyclonic flow, and around a low pressure zone we call cyclonic flow. Okay? Now to remember which direction the air is rotating around a high pressure zone versus a low pressure zone, your book actually has a really easy way to remember. All right? So here we have a little image that is representing a high pressure zone. So we're relating it to the way that you would turn a screw. If you have a screw that is high, that means that it's not in the wood and it needs to be screwed down. In order to screw down that high screw, you would need to turn your screwdriver clockwise, right? So around a high pressure zone, air rotates clockwise in the northern hemisphere. If you have a low screw, which means the screw is already in the wood, then you need to unscrew it. And in order to unscrew a screw, you turn your screwdriver counterclockwise, right? So we have righty-tighty, right, to tighten the screw in, that's clockwise motion, and lefty-loosey, that's counterclockwise motion to unscrew the screw, okay? So around a high pressure zone, we have clockwise rotation of air, and around a low pressure zone, we have counterclockwise rotation of air in the northern hemisphere. Remember that it will just be reversed in the opposite direction in the southern hemisphere. Okay, so if we go back to the image that I showed you previously with the northern hemisphere being in the winter and the southern hemisphere being in the summer at this time, we have high pressure cells that get created over land, and we have low pressure zone that's getting created over the water. Now, around these high pressure zones, the air is going to flow in a righty-tighty or clockwise manner, okay? Over the low pressure zones, it's going to rotate in a lefty-loosey or counterclockwise manner, okay? And so that has implications of where the wind is coming from along our coastal environments, right? In the winter time, we see a low pressure over the water, which means that we have rotation in the counterclockwise direction. So along the coast over here, we're going to end up having air that is moving from out in the middle of the Pacific Ocean, moving towards the coast. So that air is going to be a nice cool air. It's not going to be really cold, it's just going to be cool, so it's going to be fairly mild. Whereas if we go to the other side of the United States, in the winter time, we have a low pressure zone, and again, that's a counterclockwise movement. So the air that is coming right here is actually coming from all the way up here, which is super cold in the winter time. So along our coast, we're getting a mild temperatured wind. Along the East Coast, they're getting a very cold wind. Okay, and during the summertime, it would be reversed, where we would have low pressure over land and we would have high pressure over water. And so the direction that the air is coming from for the west coast of the United States, it would end up be coming from the north, which is around Alaska in the summertime, which again is mild. And for the East Coast, the low pressure zone is around here. And so it's a counterclockwise rotation, right? And so we end up getting, sorry, I'm saying it reverse. Sorry, you would have high pressure over here. And so the air would be circulating in this manner. So the air that flows along the east coast of the U.S. would actually be coming from down around the Caribbean. So down around the Caribbean in the summertime, it's really hot. So the east coast of the U.S. would be getting a hot wind. So if we go between winter and summer, the west coast is getting a mild wind in the winter and a mild wind in the summer. The east coast is getting a cold wind in the winter and a hot wind in the summer. So the east coast ends up having a less mild climate than the west coast does. Okay. Now, when we've been talking about rain at the equator, we're talking about a kind of a gentle rain. We're not talking about strong storms. We're talking about just kind of a daily pattern of rain, of water falling. But generally where we see actual storms created is where we have air masses that are cold and air masses that are warm meeting. And that occurs between 30 degrees and 60 degrees north or south latitude. So when you have warm air mass moving into an area that's already occupied by a cold air mass, then we call that a warm front. And when you have a cold air mass that moves into an area that's occupied by a warm air mass, we have what's called a cold front. So whether the way that the warm air is brought into areas of cold air and cold air is brought into areas of warm air is due to the meandering of something called the jet stream, which is a band of wind that flows just above the troposphere, I believe, and it flows towards the east, and it meanders so that it moves to the south and it moves to the north. And we actually have multiple jet streams that move along our planet. Okay, so here's a little image of what happens when you have a warm front come in versus a cold front. Okay, so we have an area that is occupied by cold air, and now you have warm air that moves into it. Remember that warm air is generally going to be more moist than the cold air is. So when the warm air comes in and it hits that cold air, it's less dense, so it gets pushed up, and it also cools down, which makes it release rain. And so we end up having kind of a gentle rain that falls in a warm front. Whereas a cold front, you already have warm, moist air, and then you have cold air that comes in. And that cold air makes it so that you have, that pushes the warm air up kind of rapidly, and that causes a sudden release of rain, and that leads to violent rains and thunderstorms. So this would generally be what you experience in places that are normally colder temperatures, so higher latitudes. This would be what you would experience in places that are generally warmer temperatures, so the lower latitudes, meaning around the equator up to 30 degrees and maybe 40 degrees north or south. Okay, so this jet stream, we can see that there are multiple jet streams. So as this band of air moves, it kind of meanders to the north and it meanders to the south. When it meanders to the south, it's bringing cold air down to areas that are occupied by warm air normally. When it moves towards the north, or I should say the subtropical jet stream, when it moves towards the north, it's bringing with it warm air to areas that are occupied by cold. Okay, so we end up having a warm front coming in, being brought up by the subtropical jet stream. We end up having cold fronts being brought down by this mid-latitude jet stream. Okay, so the jet stream forms between the circulation cells that I showed you previously. So again, this image here is just looking at our Earth from the side, like that first lecture video that I showed you. So the green represents land, and this would be all the atmosphere, or the troposphere, I should say. And so we can see the equator, air is rising, 30 degrees, air is falling, 60 degrees, air is rising, and the North Pole, air is sinking. Okay, so you have these cells that get created, which are called the Hadley cell, the Ferrel cell, and the polar cell. But I'm not going to require you to remember the names of those circulation cells. Okay, so just to show you where the subtropical jet stream is, it goes around 30 degrees north, and it basically can bring air up this way into where it's normally colder. And then you have this polar jet stream, which can bring air that's colder into areas that are warmer. Okay, so in this image, this is the Atlantic Ocean. Here's Florida, here's Cuba, here's the Gulf of Mexico in here, and this would be the Caribbean Ocean down here. So we see this band of wind that you should all be familiar with around now. Well, at least when I'm recording this lecture, because we have had quite a few hurricanes happening, and I just basically gave you kind of the answer. So is this cyclonic or anticyclonic? What you should have said is it is cyclonic. And is this a low pressure system or a high pressure system? It would be a low pressure system. Okay, so the winds are actually rotating counterclockwise and in the northern hemisphere, counterclockwise rotation occurs in low pressure systems. Okay, so what causes this to occur? Well, I have a video that is the next video in the series of videos you should be watching. It's actually the final one. It's on hurricanes. And that will give you a little more information about what causes hurricanes to occur. But essentially what happens is you have a low pressure area that gets created because of the warm temperature, usually over the ocean, because you have warm temperatures and moisture. So when you have warm temperatures and you have moisture, which is caused by evaporation, then you have air that rises in an area, okay? And when you have air that's rising in that area, you have winds that end up converging, and with the greater amount of heat and moisture, those winds start converging and rotating even more rapidly, okay? And so that pushes the air up, and that air, remember, is moist, and so once it gets into the colder upper atmosphere, it comes back down and releases the rain that it can't hold anymore. Okay, so you end up having a rainy and windy condition that gets created, which we call, first step we would call a tropical storm, and then as the winds increase, then you would get to hurricane ratings, which basically go from 1 to 5. Okay, so these occur in generally between 15 degrees and 20 degrees. And the reason why it occurs between 15 degrees and 20 degrees north or south latitude is due to the temperature of the water, and also due to Coriolis effect. You can't really have hurricanes without Coriolis effect, and that's why you don't have hurricanes at the equator. You have them just north or south of the equator because you need that rotation, which is caused by Coriolis. Okay, so when we have these conditions that occur in the western North Pacific, so in this image over here, right, near Asia, we call them typhoons. When they occur in the Indian Ocean over here, we call them cyclones. And of course, when they occur around the US, we call them hurricanes, all right? So they occur in ocean water that is greater than 25 degrees Celsius, and therefore they occur in the late summer to early fall because that's when the water is the warmest. Okay, this image is showing you where hurricanes generally occur and the intensity of those hurricanes that have occurred there. So what drives the hurricane is the warm water. And so I wanted to make a note, the Hurricane Harvey that recently hit Texas, Hurricane Harvey was bringing so much water that essentially it flooded the area around Houston. And usually when a hurricane comes on land, it dies out because it doesn't have the warm water to cause it to continue to power it, right? The warm water is really what powers the storm. So when it gets over land, it doesn't have that warm water anymore, and so the hurricane kind of dies out. But what happened with Hurricane Harvey is that it rained so much that it actually flooded the land. And so the land didn't act like land anymore. Instead, it acted as water. So it continued to power the storm. The storm didn't die out as quickly as it normally would when it got on land. And instead, it continued to power, it continued to release rain, and it continued to cause flooding and lots of damage. Okay, so if you guys have any questions, please post them under the weekly discussion. And of course, make sure you post one. Even if you don't have a question, post a comment or answer somebody else's just so you can get credit for the week. All right, thank you.